as you probably know, Tim Colonius works on jet, on the response of a turbulent jet to actuation, and he finds that the ensemble average response can be described by a linear system. Now you look at Jan Dusik, and he figures out that if he does this, so this is from an experiment. He looks at his numerical simulation of a jet, and he figures out that the response to input noise of a jet at upstream is linearly related to the response downstream. So essentially you have strongly turbulent dynamics, which after some ensemble averaging appears like a linear system. Do you have some thought on that?
Well, it means that this introductory lecture becomes not so introductory anymore, because you can use the same tools to study this kind of case. Normally, when you have statistical stationary signals, you tend not to work with the signal itself, but with its statistical properties. So, in fact, in the notes I described it.
Ensemble averaged. I mean, you take many different initial conditions, and then you look how for this actuation, the average response is maybe 1 second later or 2 seconds later, and this always looks like a linear system. And this kind of surprises me. We did it for the Lorentz attractor also. At some point I can tell you where the catch is, where the linearity disappears, but I find this very surprising that you have a turbulent flow where everything's supposed to be nonlinear, but if you go to the ensemble averaging, it seems to be have a strongly linear dynamics.
I guess it has to do with being strongly convection dominated. What is happening here is going to happen more or less after some time afterwards. I think we should discuss that. It's deeper than that, I guess. Other questions? Okay, if not, then we will move now to the core of this lecture. So now we have learned that complex frequencies are eigenfunctions of linear operator, which is the convolution. And these are the ones that in the DMD you've learned yesterday how to get directly from the data. So again, let's take a step back on the things that you have learned in your undergraduate course, and let's talk about the Laplace transform and the zeta transform. So definition: Laplace transform is an integral transform. You take your signal, continuous, and you integrate it from minus infinity to infinity with, you recognize this guy here is the conjugate of your complex frequency, is the conjugate of your eigenfunction, in fact. Okay, these exist if your signal does not grow faster than what an exponential can kill. So if it's of exponential order, this typically happens if you are focusing on a special region of the S-plane, which is the region of convergence, but I'm not going into too much detail on that. What I want you to see is that here you're doing, again, a mapping. So I give you an S, and for every S, well, you are in your S-plane. Let's say if the sigma is 0, I have a Fourier mode. As we said, if sigma is negative, your thing will decay, otherwise it will explode. And if you have no imaginary part, this will just not oscillate and vanish or explode. And now, geometrically, I've introduced before the notion of inner product, and if you look at this Laplace transform, what you're doing is in fact an inner product. So in this case, the basis on which you are doing the comparison process that we have seen before is a basis of eigenfunctions of the linear operator. Okay, so in this case, you are for every S, you are comparing how much your signal looks like that particular eigenfunction of the system. Okay, you have plenty of eigenfunctions. You have an entire plane. Okay, and if you want to do data compression, that is definitely not what you are looking for. But in principle, for any S, you are just comparing your signal with your basis that exists in that point, and you tell how much of that you have there. And of course, well, some properties that we'll need later, you might remember that the Laplace transform of a derivative brings just a multiplication by S, and the Laplace transform of an integral brings just 1 over S. But we will use this later briefly. Now, the notion extends to the discrete case. In this case, we have the zeta transform, and we have the same definition that we've seen before, but just we have to be careful about the definition, the link between real frequencies and complex frequencies. Now, in our zeta plane, Fourier modes are with rho equal 1, and you've seen this circle a lot yesterday. You remember when Professor Smith was showing the DMD mode, was showing, they are very close to the circle, so they're close to Fourier, and then Professor Noack asked, yeah, but then what is the main advantage of using the DMD over the DFT if you're always on the circle? Okay, here's where it's coming from. If you have points outside the circle, explosion, inside, vanishing, and then you're going to have vanishing without or explosion without oscillation here. And again, you're projecting, you're comparing for every point in zeta what is how your signal looks, how closely your signal looks like that specific eigenfunctions. But again, here you have infinite possible zetas, and through the DMD you don't look for infinite possible eigenfunctions. You look for very special ones, and you look for the ones that corresponds to poles of a system. How many of you remember the notion of pole? Well, good, a lot. Okay. Okay, for the zeta transform, shifting backward or upward brings a term zeta or zeta minus 1, similarly to Laplace. And now about the mapping between discrete and continuous frequencies. So you take your discrete signal. Of course, here I'm playing with 1D things, right? In the case of the DMD, you don't have just one point. You have maps. Your signal is a MIMO. It's a MIMO system, in fact. But what is happening behind the line on the time domain is more or less the same notion that I'm describing here. So you take a discrete signal, which is a linear combination of impulses. You write it as a continuous one, and then in the continuous one, you can take the Laplace transform. You do a little bit of arrangement, and you get that the Laplace transform can be seen as a zeta transform only if you introduce, again, your time discretization in your exponential. And again, as I said, exponentials becomes powers. So you can link complex frequencies from the Laplace with the complex frequency from the zeta thanks to this mapping. And this mapping, if I write it here, has some very special properties. It's a conformal mapping, in fact, but we will not enter into these details. It simply tells you how to convert a continuous frequency into a discrete frequency, and this was the line that you've seen yesterday in the DMD algorithm. Okay. So again, this mapping is really the essence of our continuous world, which exists only when we write down our equations, and the discrete world, which exists when we take some data. So let's say it's important to understand this mapping. So if I tell you I have a sigma which is highly negative, what does it mean in this case? If I write down this in terms of amplitude and frequencies, this simply means e to the minus something. So this is going to be like a tiny circle. And if I move this thing towards the left, the tiny circle will vanish at the origin. So the minus infinite on that side is the origin on the other side. Similarly, if I take a positive guy here, I get a big circle. And if I take now horizontal lines like a frequency, negative frequency or positive frequency, doing this mapping, what I take is just angles. Which means, again, that now if I take this guy and I move it up and up and up, this will move like this around the circle. But then after some moment, it will come back to the same point. And that is what you've seen in the example of before. This is, again, the notion of aliasing. Okay. So now, convolution theorem comes from everything that I've told you. I will not derive it. But let's say that you have your system. You project your system into the basis of eigenfunctions of the system. So you do a zeta transform. You do the same for the output. And now we have seen that for every frequency, the system will respond doing just a multiplication. And that is simply by the transfer function. Okay, so the transfer function is a collection of eigenvalues of your system. Every frequency has its associated eigenvalue, and if you plot the frequency versus associated eigenvalue, you're plotting the transfer function. So in the frequency domain, of course, the input-output is a multiplication, and since you know that in the time domain is a convolution, then you know the link between convolution in the time domain is a multiplication in the frequency domain, and you can beautifully show the opposite, but I'm not going to do it here. Basically, the convolution, I just tell you, is a polynomial multiplication. And from there you can see very fancy things. Which now brings us to differential and difference equations. You can see it like that. If you're doing system identification, say you have a lot of data. You have chosen your favorite expansion. You project your data into the spatial expansion, and now you have a temporal evolving coefficients. Okay, and now you want maybe to fit some dynamical system into that. What you have are time varying sequences. Okay, you're in the discrete domain. You might use your favorite regression tool, and you can see how to link this to a certain coefficient that can tell you how the system will evolve. And for that, then you can go back to the continuous world by using the mapping that I've shown you before. Okay, that's a bit a big picture. So a linear system can be described in terms of differential equations. That's definitely not the most efficient way to represent them. Tomorrow you will learn a much better one, I think, but this still gives you a bit the picture. It's an ordinary differential equation. Here I'm taking derivatives. Okay, so this is the nth derivative. I have nb of these terms, and so nb is also the order of the ordinary differential equation. And here I have a linear combination of derivatives of my inputs. These are called feedback coefficients and feed-forward coefficients. Okay. You heard about feedback control and feed-forward control. Well, feedback control means that I don't like the way this guy looks in my system and I want to change them. And so I will take something from here and move it back here so that I manipulate this guy. In feedback control, you control the feedback coefficients. In feed-forward control, then you don't like these guys and you change these ones. Okay? If you're doing digital filtering, you will look for what is the best combination of these guys that gives you the frequency response that you're looking for. Okay? Everything falls more or less in the same picture. That's why we really wanted to give this introduction today. You need to have this condition if you want your system to be realizable, but I also want to skip this detail for the moment. This simply means that the system has to be causal. It cannot be anti-causal. It cannot predict the future. Okay? You should not answer a question before I ask it. Okay? Be causal. Now I project this problem, and again, you've heard about Galerkin project and things like that, but in a way you've learned this in much before. You take your ODE, and now you project it onto the basis of eigenfunctions of your linear problem. You have too many of them, but so this becomes continuous, and that's what you don't like in a real case, but the principle is the same. What it means, I'm just computing the Laplace transform of this whole thing, and this is a linear operation, so I can just compute the Laplace transform of derivatives. You remember that this brings terms in S, so all of that becomes a polynomial in S. You have a polynomial in S on the other side, so your transfer function is going to be the ratio of two polynomials. Of course, you have poles when you have zeros of the denominator. So these are the things that leads to resonance and that make the Oklahoma Bridge fall, for example. And these are the guys that are killed. Is your perfect filter. If you hit at zero, that guy is going to be knocked out perfectly. Okay, it will not come out of the system. It doesn't work like that when you design a filter, but the notion is a bit the same. And then what I will ask you to keep in mind is the link between this and that. So let's say that I give you a transfer function. You can tell me what is the ODE behind that, okay? Because of this mapping. And I will show you this also later. You can do it in the discrete case, and the discrete case is the one you came here for. In the discrete case, you have we have difference equations, okay? So what you're saying is that a combination of your output at this step and some steps before is equal to a combination of my input at this step and some steps before, okay? And so from here I can take my current time step and I write what is called a recursive equation. And those of you who like time series analysis will see this everywhere in economics and in many other applications, okay? So what you're saying here is, again, the very essence of linearity. What is happening now is a linear combination of what was my input before and a linear combination of what happened before. So let's say that now I give you a system that has no input. Maybe starts from some initial condition and will alone, if it's stable, it will decay to some point. So let's say that these guys are not here. What you're saying is that what happens now is a linear combination of what happens before. And this is, you've seen it yesterday. You remember in the companion matrix, the last column, where you were taking a linear combination of previous time steps to see what is happening right now, is again a notion that is coming from the assumption of linearity. Okay. So again, you can project this problem into your zeta bases, you arrange it, and you have your transfer function, which looks slightly different in a discrete case because your polynomials are in terms of zeta to the minus something, but you can arrange this. And again, you have zeros and poles, which I indicate for a discrete system with zeta and pi. Okay. So this brings me to the question I asked, and let's say a simple exercise that you will do during the coffee break, for example. So you take the system from before, you know the impulse response, so you know everything about this system. I gave you the impulse response in analytical form, so you know the equation. So from this impulse response, you can compute the Laplace transform, and now you have your transfer function. From your transfer function, it has to be a ratio of polynomials, so you have the coefficients on the top and the coefficients on the bottom. And so you can tell me what is the ODE that is driving that system, okay? If you use the mapping, the conformal mapping that I've shown you before, you can move from S to zeta, and now you have your transfer function in the discrete world, which is also a ratio of polynomial. And from that, you can find your recursive formula, okay? That is the easy part. What you came here for is to learn how to do the opposite. So now I give you data. I give you a lot of U and a lot of Y. You run your favorite least square regression or whatever, and you get these coefficients. From these coefficients, you know the transfer function. From this one, you can map it back to the continuous, being careful about aliasing. And then you can tell me what is the ODE that is in the data that you have seen. Okay? So I think I will take some questions if you have. Okay. So by the way, there are 5 or 6 Python exercises associated to these nodes. They are all already available together with the slides in the folder. So go with them, play with them. You might find the solution for most of the exercises that I'm asking here, but not all of them. So harmonics and frequency analysis. You've seen that in the Laplace or zeta domain, things can explode or vanish. And that sometimes is not what you're looking for. So you move from Laplace to Fourier. There are some key differences. You lose something, you gain something, as usual. In the case of Fourier, what you will do, you will take your S-plane and forget about everything, but just you take only the imaginary axis. And in the discrete one, you will just look at the circle. Okay? So you're taking now a very much reduced set of possible eigenfunctions. Okay? They lie in a manifold that has the same dimension of the time. Okay? So now it becomes much easier in terms of mapping and filtering and things like this. So the Fourier transform is defined like that. Basically, I just took S and I put S equal to, I said sigma is 0 and rho is 1. There are a lot of dangers in doing that because you are killing the exponential guy that was ensuring that your conversion works if your signal is of exponential order. Conclusion, convergence now becomes a problem. Okay, most of the many signals don't have a Fourier representation. So what you do in this case, you cheat a bit and you add some additional constraints to make it work. So this can only work if your region of convergence lets you do that. So if the region of convergence includes these guys, then you can move from Laplace to Fourier by just replacing S with e to the e omega and replacing zeta with e to the e theta. Okay. Now, as we've seen, if we take the circle, now we have the problem of aliasing. If I go from, let's say, minus pi to pi, I have my spectra, which for a real signal is going to be symmetric. And then it will start over and over again. That's what you want to avoid, because if you have aliasing, it means that this guy comes a bit on the other side. So let's say that you don't have aliasing and you have a periodic signal extended there. This is a continuous function. Okay, here theta is continuous. I said no constraint on theta. I said I can take any theta in the circle. So it's a continuous transform of a discrete signal. Okay. Now I say, okay, well, there is nothing like a continuous thing in data processing, so you have to discretize that. And I say I will take uniformly spaced frequency beams in the circle. So now your Fourier transform is becoming a Fourier series because you have a finite number of frequencies. And so you are automatically saying that your signal is periodic. And that lets you forget about all the problems of convergence, okay? But brings other problems, which is the windowing. So what is happening, I'm saying that my signal starts over with a periodicity of t, where t is my observation time. And of course, if your signal does not behave gently at the junction, you will create discontinuities and your spectra will look noisy and you will have problems, okay? That you can limit doing some windowing, some other things, but for the moment, just take the picture. This is coming because you said that the frequency have to be uniformly spaced. The DMD does not say this, does not ask for that, so it can easily avoid this limitation, okay?